Evaluate the following limit and state the equation of any horizontal asymptotes. Okay, well, we've learned one trick, exactly one trick, which is that if you do a limit at infinity and it's a number over a power of x, that limit will go to 0. That's all we have to work with here, and if we try to use it in this situation, we run into a bit of a problem because here we have powers of x in the numerator and the denominator. So essentially these fight, and if you try to evaluate this thing, here's a very crude and kind of cheating way to try to evaluate this. You get 2 times infinity squared plus infinity. Don't do this on tests. This is definitely not kosher, but it's enough to give you the idea. 7 times infinity squared minus 2 times infinity plus 4. We end up with infinity. This is what we call a limit of type infinity over infinity, and those don't cancel out the way regular numbers do. Infinity over infinity is technically undefined. Even the fact that these are both infinity squared isn't enough to cancel them out. That isn't safe to do in general. So we can't do this just by thinking of the x's as infinities. We need something else. Good news, there is a way to handle these. It's a fairly straightforward trick. What we do is we look for the highest power of x in each one of these things and divide by it. So if we have, I'm just going to recopy this a little bigger. La 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 la. 7x squared minus 2x plus 4. The highest power of x in either of these things is x to the 2. I'm going to divide every single one of these by x to the 2. Or you can think of it as factoring out an x to the 2 if you want. So in the numerator, I'm going to go 2x squared divided by x squared plus x divided by x squared minus 5 divided by x squared all over. Now if I divided the whole numerator by x squared, I must do the same thing in the denominator. So 7x squared divided by x squared minus 2x divided by x squared plus 4 divided by x squared. Now, these x's we can cancel. These aren't infinities. So we can cancel those. They're just gone. We can cancel those x squareds. They're just gone. And after we do that, here's what we have. 2 plus, oh, I'm sorry, there's a few more x's we can cancel here. Here we have x over x squared. I can cancel a single x in the numerator and one of the x's in the denominator. And same here, cancel an x, cancel an x. So now we have 2 plus 1 over x minus 5 over x squared. Downstairs we have 7 minus 2 over x plus 4 over x squared. And this is still the limit, or we're trying to find the limit as x goes to infinity. This is definitely uglier than what we had before, but what's good about it is now we can invoke this limit property. We can say, okay, 1 over x, you're going to go to 0. As x becomes infinitely big, that term vanishes. 5 over x squared, that vanishes too. 5 can't keep up with an x that's getting infinitely big and is also squared. Down here, 2 over x, gone. 4 over x squared, gone. All these smaller terms vanish, and it turns out the only things that survive are the 2 and the 7. And so the limit of this function is 2/7. In other words, this is the formal way of solving this, but let's go back to the original. Could we have seen that coming earlier? Yeah, we can. It turns out when you have an expression like this, as x gets very big, the highest powers of x take over, and all these lesser powers of x can't keep up. They get left behind. Imagine if x is 1,000, then here we'd have 2 times 1,000,000 plus 1,000 minus 5. This term is getting much bigger than the others to the point where you can ignore them. Compared to this 2x squared, this term is too small to matter. This term is too small to matter. the minus 2x and the 4 are too small to matter. So really, this limit just comes down to a fight between 2x squared and 7x squared. And the ratio of those two terms is always going to be 2 over 7. The x squareds will always cancel each other, and the 2/7 is the only part that will survive. So if you have a polynomial over another polynomial, it's going to come down to the highest power of x in the numerator versus the highest power of x in the denominator. And all the other terms disappear. They end up being too small to matter. And that's the tactic we're going to use to get all of these horizontal asymptotes. Let's see, I'm debating whether I want to try to sketch this. I don't think I will right now. They didn't ask us for a graph, and I'm sure that's going to come up later. But if we were doing a graph for this thing, that would mean that in addition to whatever vertical asymptotes it might have and any intercepts it might have, you could put in a horizontal line at 2/7, which is like 0.28, or 0.29, sorry. And the function out at its ends would have to somehow settle down next to that line. In the middle, it might even cross that line, but eventually it's going to settle down and approach that line asymptotically.